Today we're explaining neural networks, not the sanitized textbook bullshit where everything magically works. The real version where your gradients vanish, your loss explodes, and you spend 3 days debugging why your network thinks every image is a hot dog. 3 AI engineers, 1 mathematician who's seen too much, and the brutal truth about teaching sand to think. I'm Sam, and someone's definitely crying by the end.
I've trained over 500 neural networks and watched 400 of them fail spectacularly. My first network was supposed to recognize cats versus dogs. After 72 hours of training, it achieved 50% accuracy, literally worse than random guessing. Turns out I forgot to normalize my inputs. Every pixel value was between 0 and 255, and my network was having seizures trying to process that chaos.
My masterpiece was a language model that was supposed to write poetry. Spent 6 months tuning it, fed it Shakespeare, Whitman, the classics. Final result, it generated banana, 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 banana for literally every prompt. Turns out my tokenizer was broken, and it thought the entire English language was just fruit names.
Everyone wants to know how neural networks think. Here's the uncomfortable truth: they don't. They're just matrix multiplication on steroids, finding patterns in data through brute force math. But somehow this mathematical chaos learns to recognize faces, translate languages, and beat humans at chess. It shouldn't work, but it does, and nobody really knows why.
Elena, you're our guide through this mathematical hellscape. Sarah and Marcus, you get to suffer through explaining this to normal humans. No mercy, no hand-waving, just pure neural network trauma.
Let's start simple. What is a neural network?
It's like a brain, but made of math, neurons that fire and connect and...
Stop, it's nothing like a brain. That analogy has poisoned an entire generation of AI students. Try again.
Okay, it's a function approximator. You feed in numbers, it does a bunch of matrix multiplications and nonlinear transformations, spits out different numbers.
Better, but what kind of function? How complex can it get?
Universal function approximator. With enough neurons and layers, it can approximate any continuous function. That's the theory anyway.
Yes, the universal approximation theorem. Do you know what enough neurons means in practice?
More than you can afford. For any real problem, enough usually means billions of parameters and computational costs that make your AWS bill look like the GDP of a small country.
Exactly. Now explain how these magical functions actually learn.
Gradient descent. You calculate how wrong your network is, then adjust the weights to be less wrong. Repeat until it works or you run out of patience.
How do you calculate how wrong for a function with millions of parameters?
Backpropagation, you use the chain rule to compute gradients backwards through the network. The math gets really ugly really fast.
Show me. Calculate the gradient for a 3-layer network with Ray-LU activations.
Jesus Christ. Okay, loss function L, output layer Z3, hidden layers Z2 and Z1. Equals delta L slash delta Z3 slash delta W3. Then delta L slash delta W2 equals delta L slash delta Z3 slash delta Z2 slash delta W2. This is why we have automatic differentiation frameworks.
What happens to those gradients as you go deeper?
They vanish. The chain rule means you're multiplying lots of small numbers together, so gradients get exponentially smaller as you go backwards. Deep networks couldn't train for shit until we figured out better activation functions and normalization.
Or they explode. Explain why gradient clipping exists.
Because sometimes gradients become huge and your weights jump all over the lost landscape like a drunk kangaroo. Your network goes from 80% accuracy to completely broken in one update step.
Good. Now explain what the network is actually learning during training.
It's learning features. Early layers detect edges and simple patterns. Deeper layers combine them into complex concepts like faces or objects.
That's the story we tell ourselves. How do you know that's what's happening?
We visualize the activations, use techniques like GradCam to see what parts of images the network focuses on.
And when you do that, what do you usually find?
Chaos, complete fucking chaos. The network focuses on weird texture patterns, background objects, sometimes just random noise. It's making the right predictions for completely wrong reasons.
Exactly. Neural networks are alien intelligence. They solve problems, but not the way humans do. Now explain overfitting.
The network memorizes the training data instead of learning general patterns. Gets 100% accuracy on training set, 50% on test set. It's like a student who memorizes all the practice problems but can't solve new ones.
Why does this happen?
Too many parameters, not enough data. If your network has millions of weights but only thousands of examples, it has enough capacity to just memorize everything.
How do you prevent it?
Regularization, L1, L2 penalties, dropout data augmentation, early stopping. Basically torture your network until it stops being so clever.
Dropout is interesting. Explain how randomly breaking your network makes it work better.
During training, you randomly set some neurons to 0, forces the network to not rely on any single neuron too much. It's like teaching a team sport by randomly benching players. Everyone has to learn to work together.
Now the big question: why do neural networks work at all?
That's the million-dollar question, isn't it? We have theories about implicit regularization, lottery ticket hypothesis, neural tangent kernels, but honestly, we don't really know.
We've built the most powerful AI systems in history, and we don't understand why they work. Comfortable with that.
Absolutely not, but they do work spectacularly well for many tasks. It's like medieval doctors who didn't understand germ theory, but still figured out that certain herbs helped with infections.
Except our herbs can write poetry, drive cars, and might eventually control critical infrastructure. Final question: what's the biggest misconception about neural networks?
That they're intelligent like humans. They're pattern matching engines, incredibly sophisticated ones, but they don't understand anything. They just find statistical regularities in data.
And that they're magic. Every breakthrough feels like magic until you dig into the details and realize it's just better data, more compute, and clever engineering. The math is beautiful but not mystical.
Holy shit, so we've built these alien intelligences that work through mathematical brute force. We don't understand why they work, and we're using them to make increasingly important decisions about the world.
Welcome to the current state of AI. It's simultaneously the most impressive and most terrifying technology ever created. We're riding a tiger we can't fully control.
This episode was brought to you by Unstruct AI, where we explore the gap between the AI hype and the brutal mathematical reality. Because understanding the limitations of our tools is just as important as celebrating their capabilities. We're back, let's dive into the practical nightmare of actually training these things. Sarah, what's the most frustrating part of neural network development?
Hyperparameter tuning. Learning rate, batch size, architecture choices, optimization algorithms. There are thousands of decisions, and most of them are made through expensive trial and error. You can spend weeks training models that don't work because your learning rate was 0.01 instead of 0.001.
The debugging is insane. Your network isn't working, but why? Is it the data, the architecture, the learning rate, a bug in your code? Unlike traditional software where errors crash the program, neural networks just silently produce garbage.
And the compute costs. Training large models requires ridiculous amounts of electricity and specialized hardware. GPT-3 training cost an estimated $5 million just in compute. That's not democratized AI.
What about the data problems? Everyone talks about algorithms, but what about the fuel these things run on?
Data is everything, and data is garbage. You need massive amounts of clean, labeled data, but most real-world data is biased, incomplete, or just wrong. Garbage in, garbage out, but with neural networks the garbage might look convincing.
And data preparation takes 80% of your time. Cleaning, augmenting, balancing classes, handling missing values. The sexy part is building the model, but the real work is data plumbing.
Plus ethical issues. Training data often reflects historical biases. Your objective AI system inherits all the prejudices baked into human-generated data. We're automating discrimination at scale.
Let's talk about the elephant in the room: interpretability. We're deploying these black boxes in high-stakes decisions.
It's a nightmare. You can make a model that predicts medical diagnoses with 95% accuracy, but when a doctor asks, why does it think this patient has cancer? Your answer is because these 10,000 numbers said so.
We have techniques like LIME, SHAP, attention visualization, but they're all post hoc explanations. They're telling stories about what the model might be doing, not what it's actually doing. It's like reading tea leaves.
And there's a fundamental trade-off. More interpretable models are usually less powerful. The models that work best are the ones we understand least. We've created artificial intelligence that's genuinely alien to human reasoning.
What about the future? Where are neural networks heading?
Bigger, always bigger. More parameters, more data, more compute. We're in an arms race where progress means throwing more resources at the problem. It's not sustainable indefinitely.
But also more specialized. Instead of one giant model for everything, we're building models optimized for specific tasks. Edge computing, mobile deployment, real-time applications, efficiency matters more than raw capability.
And hopefully more understandable. We need neural networks that can explain their reasoning, show their work, admit uncertainty. Right now, they're overconfident bullshit generators with no concept of what they don't know.
Any final warnings for people who want to work with neural networks?
Learn the fundamentals. Don't just import TensorFlow and pray. Understand linear algebra, calculus, probability. When your model inevitably breaks, you need to know why.
Start simple. Everyone wants to build GPT-4, but you should master linear regression first. Most real problems don't need deep learning. They need clean data and good engineering.
Stay humble. Neural networks are powerful tools, not magic. They're pattern matching engines with impressive capabilities but fundamental limitations. Respect both their power and their blindness.
And remember, we're building systems that will shape the future of human civilization, and we don't fully understand how they work. That should be both exciting and absolutely terrifying.
Thanks for the brutal reality check, Elena. Now I'm going back to hyperparameter tuning and hoping my GPU doesn't catch fire.
And I need to explain to my boss why our simple image classifier needs 3 months and a budget the size of a small spacecraft to train properly.
Keep building, keep questioning, keep pushing the boundaries, but also keep asking whether we should, not just whether we can. The future of AI depends on thoughtful engineers, not just clever ones.
This has been Unstruct AI, where we explain how neural networks really work, through mathematical brutality, computational excess, and a healthy dose of uncertainty. Until next time, remember that intelligence might be stranger than we think.